So, how do you actually make a plan when literally everyone else is planning against you? I mean, really think about it. Whether you're just trying to merge onto a jam-packed highway during rush hour, or we're talking about algorithmic bots executing millions of trades in a fraction of a second, we are constantly navigating a world where independent agents are plotting totally conflicting paths for limited resources. The big question is, how do we keep all these competing plans from just collapsing into total chaos?
Well, welcome to this explainer. Today, we're diving into the evolution of the plan. We're going to uncover the invisible mathematical rules that actually govern strategic decision-making in our daily lives. From basic human conflict right up to the absolute cutting edge of artificial intelligence, we're going to see how systems are designed to force competing, completely selfish plans to actually work together perfectly.
Okay, so here's our game plan for today. We'll start with 1, the ultimate planning problem, then hit 2, mechanism design and cake. Move on to 3, algorithmic game theory. 4, fast planning and chaos. 5, balancing multiple objectives. And wrap up with 6, the future of planning. All right, let's jump right in.
Section 1, the ultimate planning problem and the foundation of strategic interactions. Because, almost every complex system we interact with, we're talking traffic networks, communication grids, power systems, is actually just a massive web of selfish agents making competing plans. Everyone naturally wants the fastest route, the cheapest power, the most bandwidth.
And this brings us directly to game theory. Now, by definition, game theory is a mathematical model of strategic interactions among rational, intelligent agents, where each agent's decision directly affects the other's payoffs. The central hurdle here is ensuring collective efficiency. Like, how do we build an optimal, smooth-running system when everyone in it is basically just a selfish utility maximizer? They're not trying to help the system at all. They are just executing their own plan to get the biggest piece of the pie for themselves.
Which leads us to Section 2, mechanism design and cake, where we essentially reverse engineer the rules of the game. If game theory is playing the game, mechanism design flips it and asks, how can a centralized social planner design the rules from the top down so that those selfish plans naturally lead to an optimal global outcome?
Let's anchor all this math in reality with a classic example, dividing a cake between 2 kids. If you, as the parent, just guess what's fair and cut it, someone is definitely going to be unhappy. But look at the divide and choose mechanism. The rule is simple. One child plans exactly how to cut the cake into 2 pieces, fully knowing that the other child gets to pick their piece first. Because of this one rule, the first child is literally forced to plan a perfectly equal cut. It's brilliant. A simple rule forces 2 conflicting, totally selfish agents to create a perfectly fair plan.
Now, what's really interesting here is how the mechanism acts as this sort of invisible machine right in the middle of the process. You have agents bringing their own private preferences, that hidden information about what they truly want. The mechanism takes those private inputs and spits out optimal decisions and allocations. It seamlessly aligns that hidden information to maximize the welfare of the whole group. And, this is key, it does this without ever actually needing to trust the agents themselves. All right, Section 3. Algorithmic game theory. This is where we scale things up from humans to algorithms. Because what happens when the agents aren't kids arguing over cake, but autonomous computer programs making rapid-fire, insanely complex plans all at the exact same time? Just look at the sheer computational scale we're dealing with here. We've got our mechanism mapping preferences, sure, but check out the vast classification of games: cooperative, non-cooperative, sequential, simultaneous, zero-sum. We are talking about computers having to calculate plans for literally millions of potential algorithmic moves, and they have to do it in real time.
So let's actually slow down for a second to look at how this builds to our next core concept, the Nash equilibrium. Out of all these incredibly complex interactions, this is the holy grail of planning. A Nash equilibrium is a state where every single player's strategy, their master plan, is the absolute best response to the strategies of all the other players. When you hit this state, no one has any incentive to deviate. Every agent's plan perfectly counters everyone else's plan. It is a state of total, mathematically proven stability.
But, as we all know, the real world isn't static. It's messy. That brings us to Section 4, fast planning and chaos, and adapting plans in dynamic environments. Random stuff happens, the environment is constantly changing, and the actions of other agents can completely shift the ground you're standing on in an instant. So how do algorithms actually plan when the future is basically an infinite tree of possibilities? Well, they use what's called sparse sampling algorithms. Think about autonomous cars or high-frequency trading bots. They absolutely cannot map out the entire infinite world. It's impossible. Instead, they use a generative model, essentially a super-fast simulator, to look at a constant sparse sample of potential next states. Rather than trying to calculate everything everywhere all at once, they compute a near-Nash equilibrium locally. Basically, they aren't trying to predict the entire future, they sample just enough of it to make a mathematically sound, near-perfect plan for right now.
So the crucial point here, and this quote from the research really hits the nail on the head, is that the computational running time has zero dependence on the massive size of the state space. It effectively ignores the vastness of the environment. However, it is exponential in the horizon time, meaning the further out into the chaotic future the algorithm tries to plan, the more the computational difficulty just absolutely skyrockets. Planning super far ahead in chaos? Yeah, that's incredibly expensive mathematically. And that brings us to the real climax of this explainer, Section 5, Balancing Multiple Objectives. This is the ultimate real-world hurdle, because let's face it, agents rarely just have one single goal. A financial trading bot doesn't just plan for profit. It has to balance maximizing profit against minimizing risk at the exact same time. Now, this creates a massive problem. In a single objective Markov game, you're just maximizing one simple fixed number. Easy enough. But in multi-objective Markov games, or MOMGs, agents are balancing diverse vectorial rewards. Think of an autonomous car. It doesn't just want to reach its destination super fast, it wants to do it without getting a speeding ticket and without spilling your coffee in the backseat. And the crazy part? Their optimal trade-off is dynamically tied to the actions of every other driver on the road. Their decision spaces are completely and inextricably linked. The solution to this giant, multi-layered puzzle is the Pareto-Nash equilibrium. Simply put, this is a state where no agent can unilaterally improve one of their goals without sacrificing performance on another one. It perfectly merges the strategic, locked-in stability of the Nash equilibrium with the rational, multidimensional trade-offs of Pareto optimality. It's essentially a perfectly balanced web of multi-objective plans. Finally, we reach Section 6, the future of planning. Specifically, decoupling exploration from planning. You see, computing that entire Pareto-Nash front for complex systems is an absolute computational nightmare, if the system has to start completely over every single time a preference changes. So how do modern algorithms actually handle this?
And this right here brilliantly illustrates a real game changer in multi-agent reinforcement learning, the two-phase preference-free algorithm. Step 1 is a massive preference-agnostic exploration phase. The algorithm isn't trying to achieve a specific goal yet, it's just exploring to build an incredibly robust model of the world. Then, step 2 is on-demand planning. Because the algorithm invested so heavily in deeply understanding the world first, it can compute the Pareto-Nash equilibrium for any specific preference almost instantly. And the best part? It does it without needing to collect new samples or learn from scratch. The major paradigm shift here is moving away from trying to learn a single equilibrium, and instead, learning an accurate model of the entire game itself. So why does this actually matter for you and me? Because these exact planning algorithms, the ones capable of instantly calculating these perfectly balanced multi-agent trade-offs, are exactly what will allow complex AI to safely route our city traffic, manage our global power grids, and stabilize our financial markets in the future. Which leaves us with one final, pretty provocative question. As autonomous algorithms increasingly take over the heavy lifting of planning our traffic, our markets, and our power grids, who is really designing the game? We've seen exactly how mechanism design shapes behavior, but as these invisible mathematical rules become the very infrastructure of our daily lives, we really have to wonder about the ultimate social planners shaping our future. Thank you so much for joining me on this explainer, and hey, keep questioning the plans happening around you.